Hi, my name is Aditya Kannan. I'm the team lead of Project 24070, and welcome to our video about the automated material sampling system. The first bagless vacuum cleaner was patented in 1980. It used a principle called cyclonic separation to separate dirt, dust, and other particles from air using a carefully tuned vortex inside the machine. You might have used one before. It's called a Dyson. But what many people don't know is that the principle behind the cyclonic separator was invented all the way back in the 19th century and is used widely today in various different scales and applications. Ethel Schmidt, our sponsor, makes cyclones of different sizes and shapes for mining operations worldwide. Some applications include mineral processing, tailings management, and wastewater treatment. Given the scale and nature of the operation of hydrocyclones, it becomes necessary to constantly monitor the composition of the output from these machines. Currently, the process of output sampling is conducted by hand, where a worker reaches into the outflow with a bucket and carefully extracts a sample that can be used for examination. This process can be time-consuming, dangerous for the worker, and inconsistent. Therefore, we designed a system that fully automates this process with the press of a button and minimal configuration. Let's have a closer look at what we've made.
So here's our design. It uses aluminum off-the-shelf components to design the frame, and then an electric motor and a idler gear that drives a rack system to propel the bucket forward. So the first component of this I'd like to talk about is our idler gear assembly. So first it uses these two pillow blocks to support our 1-inch drive shaft, and this gives us immense strength as these pillow blocks have good side load and it prevents any warpage. These are also, if you come back here, adjustable, so these holes in the rear are slotted, which gives you ample room to change the tooth engagement on this gear, as well as to account for wear over time. The next component I'd like to talk about is our motor assembly. This is one of our more simpler components. All it consists of is a motor that is attached to a gear sprocket, and this gear sprocket is what actually drives our idler gear assembly at the front. This motor, if you come to the top here, also is slotted, which allows us to change the angle of here as well as the angle of the chain. The next aspect of this I'd like to talk about is its serviceability. So this project, the main component of it was to make it easy to interchange parts and be serviced by the people working at FO Smith. So firstly, both the motor assembly and the idler gear assembly are removable with just two cap screws here at the top, two 1/2-inch cap screws, as well as the main body of the assembly is held in with these 4 main bolts, and the assembly is built off of a lighter design. And if you come around back here, you can see the guts of the assembly are all lined with UHMW, which can be removed easily once those 4 main bolts are removed. The final component I'd like to discuss is our bucket assembly. So our bucket is easily removable once it's full by means of a single wing nut in the rear, so that allows the bucket to slide out. You can dump the bucket, do what you like with it, and then slide the bucket in back into the sphere, retighten the wing nut, and that will make the bucket secure. Additionally, we have adjustment options in the rear here, so you have an array of bolted holes on both the main rack gear arm as well as the bucket support arm, which allows this bucket to be positioned however you'd like based on the dimensions of the sampler.
An ATmega 2560 microcontroller is the brain of the entire system. It reads inputs from the control panel and rotary encoder to run its software to properly automate the sampling process. This microcontroller is housed in a centrally located water and dust-tight enclosure to protect it from outside contamination, along with the rest of the important electronic components such as the battery and half-bridge controller. Wiring harnesses are then sent out to the motor assembly and control panel from this enclosure. The control panel is a slim, handheld box with knobs and buttons that control the speed, the distance, the sampling procedure, and the emergency stop procedure. The motor assembly consists of both the motor to move the sampler and the rotary encoder to track its position. Now let's bring in Sam to talk about the software that powers the automated material sampling system.
Working with the Arduino board, the bulk of our software is written in C++ and uploaded to the board through the Platform.io IDE on Visual Studio Code. The majority of our code is set up to function within a state machine composed of 4 different states: our idle standby state, our sampling state, our emergency procedures state, and our emergency wait state. The idle state is where the operator will have a control of the parameters of the system, adjusting both sampling speed as well as the distance the arm will move to the manifold that the sampling system is connected to. The sampling state will be triggered through a button on the control panel and will use the user set parameters to drive the motor and compare the distance with the embedded rotary encoder. It's also worth noting that our system's parameters will not be able to be changed mid-sample, The emergency state should only be triggered if a problem occurs in the sampling process or if maintenance is required. The emergency stop procedures should attempt to safely return the sampling cup to its initial starting position from any point unless the motor itself is where the problem is occurring, in which case it will remove power from the system, allowing for repairs to be made. If there is no current sampling taking place or the emergency procedures are complete, the system will ignore all user inputs until the emergency state is lifted. This will be the emergency wait state, which is released by once again pressing the emergency stop button. These are the 4 states that our software will change in order to conduct more safe sampling processes.
Now, to bring it all together, let's talk about how the automated material sampling not only meets, but exceeds the goals that were set out for it. Our goal for this project was to create a system that is not only fully automated, but also durable, accurate, and easy to use and service. That said, our design went through many iterations during its genesis. In fact, it initially started off as a fully fixed machine that was mounted to the inside of the launder or the collecting basin of the hydrocyclone. This meant that the rack and pinion assembly was located completely outside of the grimy, dirty, and wet environment. However, as expectations from our sponsors evolved, it turned into a much smaller but versatile device that can be mounted on the inside wall of any facility with nothing but C-clamps. But this brought us bigger challenges to make it durable, given the new conditions. Let's talk more about how our design overcomes these challenges. Since we were given the requirement that the system would be used at least once a day and would need servicing at most once a year, we successfully tested it to ensure that it can survive 500 cycles in the hydrocyclone conditions at minimum. All parts were chosen to be resistant to corrosion, as well as cheap and easy to replace in case of damage. In the rare occasion that AMSS would need servicing during its operational life, we even brought in an untrained subject to test that it could be disassembled and fully reassembled in exactly 45 minutes with solely our assembly instructions. With our well-designed code that integrates fail-safe mechanisms and real-time system monitoring, which is accompanied by easy-to-replace, off-the-shelf hardware, we know that AMSS is built to survive the test of time, but also being easy and safe to use. To conclude, our hope is that with our design, we can improve the safety and efficiency of mining operations worldwide. By replacing this time-consuming and sometimes dangerous process with a fully automated system that is easy to use, durable, and well-tested, we have great confidence in our product. Thank you very much.